Hi, I'm Gerard Fonte, and there is a clear, objective, and unambiguous solution to this paradox, although it is quite unexpected. This will be shown step by step in this video. If you haven't seen Dr. Jeffrey Kaplan's video on the Russell paradox yet, please do so before continuing here. It's available on YouTube or at his website, jeffreykaplan.org. I will be directly referencing his discussion with that assumption. His introduction to set theory is very good. Hi, I'm Gerard Fonte. I'm a mostly retired electrical engineer with over 40 years of experience. I've had the good fortune to work on a number of different projects. For the military, I've worked on missile guidance systems, electronic warfare, gravity navigation, and things that don't exist. On the commercial side, I've always pushed state-of-the-art in product design and development. I also have over 150 articles for magazines such as Elector magazine and Nuts and Bolts magazine. I also have about a dozen academic papers and conference presentations. So let's get started. The problem arises with the creation of a set. This set is the set of all things that does not contain itself. Dr. Kaplan explains the situation quite clearly. If the set does not contain itself, then the set is false because it does not contain all things that do not contain itself. If the set does contain itself, it fails the basic definition of not containing itself. This is a clear contradiction. How can something be both contain and not contain itself? Dr. Kaplan then proceeds to discuss predication in order to show that this paradox is not limited to set theory, but it's a paradox for all of language and thought itself. He works it through to the predicate, that is not true of itself, and shows that this is also a contradiction. But this is still one step away from the most fundamental contradiction of this form. That fundamental contradiction is, this statement is false. It's easy to see that if the statement is false, it must be true, and vice versa. I'm sure everyone has heard some version of this, but here's the most important thing. This statement is false can be converted to Boolean logic. And Boolean logic and digital logic are pretty much the same. Digital logic can be built. So I'm going to build a circuit that truly performs the function, this statement is false. And we're going to actually see what it does. But before we can do that, we need to take a quick tour of Boolean and digital logic. Boolean logic, also known as Boolean algebra, is based on two separate values, true, false, yes, no, 1, 0, and in the case of digital logic, plus 5 volts and ground. The difference between Boolean logic and digital logic is pretty much the fact that Boolean logic is theoretical and you have no real physical concerns, whereas digital logic is physical, and you do have a lot of physical concerns. Things such as power supply voltage, operating temperature, noise, parts layout, propagation delay, and a host of other physical and environmental concerns are necessary to get digital logic to operate properly. Let's look at a typical AND gate. Very simple, very straightforward. Has two inputs, A and B. Has one output, X. And the truth table tells you how it operates. So if input A is 0 or false, and input B is 0 or false, then the output will be false. If the input A is true and the input B is false, the output is false because, again, both inputs are not true. Same thing for if input A is false and input B is true. Again, both inputs are not true, so the output is false. Finally, if A input is true and B input is true, the output will be true. The NOT function, or inverter, is also a very trivial function. It simply reverses the input from true to false or false to true. And here's a really neat thing. If you have the AND function and the NOT function, and you put those together in enough ways, you can build any and every possible Boolean system that exists. For example, here's a diagram of a digital logic chip that you can get today for $1 or $2, and you can see it's made up of a bunch of simple gates. This circuit performs the function, and I'm not making this up, of a negative edge-triggered flip-flop. This flip-flop function can be used to build larger and more complex things. For example, you see the 4 boxes in the bottom here, which are flip-flops, and these are used to build a counter. This counter can then be used to build more and more complex things. Here's a diagram of something that I designed way back when you went to the drawing board. You actually did go to the drawing board with paper and pencil. The complexity of today's circuits is simply unbelievable. With 2.6 trillion transistors on a chip compared to the 3 transistors used to make an AND gate. Sometimes sentences can be converted into Boolean logic. For example, I like milk and sugar in my coffee. And you can see using the AND gate that the only time I really like my coffee is when there is milk and sugar in it. Finally, we get to the heart of the matter. This sentence is false is also a sentence that can be converted into Boolean logic. And here's how we do that. All we have to do is connect the output to the input. After all, if they're connected together, they have to be the same value, right? Well, there's only one way to find out, and that's to build it. So let's do that. And to do that, we're going to use this chip. This is a hex inverter. Does not mean that it counteracts magical spells. What it means is hex is 6. There are 6 inverters in this package. We're only going to use 1. So let's get started. Okay, so here we go. Building our system, very complicated. There's the chip, the inverter chip that we're looking at. That's plus 5 volts. That's ground used to power the chip. This is the input, which is now connected to ground. And since it inverts what it sees, ground is 0 volts, so it makes it to plus 5 volts. So now let's see what happens when I connect the input to plus 5 volts. And when we do that, it goes pretty close to ground within reason. And so that's looking pretty good too. That's how it's supposed to work. It takes a plus 5 volts, makes it 0. Takes a 0 volts and makes it a plus 5 volts. Okay, so now let's see what happens when I connect the input to the output. And that's weird. That's not supposed to happen. We're supposed to have 0 volts or 5 volts out. This is a Boolean system. It's got to be one of the two, but it isn't. That's peculiar. Well, this is a real head scratcher. But the problem arises because we're making a fundamental assumption. And that assumption is that these systems are static systems. But what if it's not a static system? We can determine this by looking at it with an oscilloscope instead of a voltmeter. An oscilloscope shows what happens over time. Okay, so let's see what happens when we look at it, measure it using an oscilloscope. So we've now got the input connected to a high level, and it's showing low. And now we connect it to a low level, and it's showing high, which is pretty much normal. Now what happens when we connect the input to the output? And that is definitely not normal. So what happens is this is happening here is we open this up and we see that it's oscillating. And if we look at the time between them, we are getting roughly 20 nanoseconds, which is pretty quick. That's about 50 megahertz. So what's happening is that it's switching from high to low as fast as it possibly can. Now, it's not full scale, but that's because of the limitations of the device, physical limitation. Now, if we slow this down a little bit by adding 2 extra components, we can see something different. I'm going to add 1 resistor and 1 capacitor so that the system will operate in a more normal mode. And when I do this, we see that we've created a very nice square wave oscillator. The importance of oscillation cannot be overstated. Another name for this is periodic motion. It's everywhere. It's a critical component in how the universe functions. Our hearts beat with periodic motion. So does a pendulum. Light is a photon that oscillates between a magnetic field and an electric field. Planets orbit periodically. Without oscillation, the universe on a subatomic scale to the galactic scale would not exist as we know it. So when Dr. Kaplan said it's a paradox for all of language and thought, he was really and truly significantly understating the situation. Fundamentally, the creation of an oscillator changed the system from a static system to a dynamic system. Dynamic systems change. Static systems don't. Boolean logic is always considered to be static. I have never seen any reference to an oscillator being developed through Boolean logic, even though Boolean logic has the same theoretical capabilities as digital logic. This illustrates a huge difference between systems that are perceived to be being static and those that are not. To this point, set theory is perceived as being static. However, the addition of an oscillator changes things. It can now be considered a dynamic theory. Does that make a difference? Can set theory be used to construct dynamic systems like digital logic? I have no clue. But it appears to be a door into something new. Any explorers out there? But getting back to the specific task at hand, I think it can be seen that there is a common thread in this statement is false, is not true of itself, and X is a set that does not contain itself. All apply negative references to itself, and this is sufficient for oscillation. We saw this with a simple experiment with the digital inverter. So in the end, we see that Russell's paradox is not a bug. It's a feature. In order to fit oscillators into set theory, we have to add another rule. And it seems to me this rule is painfully obvious. Rule 12 is, sets can vary over time. This eliminates a paradox because oscillators go back and forth between states over time. But more so, it is clear that sets do vary over time. The set of all cats changes. Old cats die and new cats are born. There are uncounted sets that change over time. I know what you're thinking. Now that time is involved in set theory, don't we have to be concerned with time paradoxes? And the answer to that is no. This is because there are no time paradoxes. None, zero, zip, nada. This can be shown with physical measurements, but we'll save this for later. If you liked this video, please send a note to Dr. Kaplan. If you didn't, send a note to me. You learn a lot more from your critics.